Hi everybody, and welcome to exercise 1. We're looking at page 30 of the workbook, and this is an exercise in estimating some partial derivatives in a particular situation. So let's read this problem together. So let capital T be a function of little x and little t, where capital T is the temperature in degrees Celsius of a room t minutes after a heater is turned on at a distance of x meters from the heater. And we're given a contour plot of this function over here to the right. Okay, let's just take a minute just to pick through the diagram that we have here. So we've got distance away from the heater down here on the horizontal axis. We've got time elapsed on the vertical axis. And then the contours are giving us the actual values of temperature. Okay, so like this 30, for example, represents 30 degrees Celsius in the room. Okay, and if we look at what they're asking us in part A, they'd like us to estimate fx at 10 and 25. In words, that would be the derivative in the x direction at a position of 10 meters from the heater and a time of 25 minutes. Okay, let's see if we can find the associated point over here on the contour plot. Okay, so we're talking about x equals 10 and t equals 25, so that would put us here. And you can see from the contour that we've got a temperature of 25 degrees Celsius at that point. Okay, so how would we estimate the rate of change of the temperature in the x direction? That's what they're asking us for. Okay, so moving in the x direction would be like moving left to right in our diagram. We want to estimate how fast the temperature is changing in that direction. Now, first of all, what do you think? Does it look like the temperature is getting bigger or smaller in that direction? Okay, we're moving from a contour of 30 at the beginning. I'm going to label that point R. Okay, we're going through our point and we're winding up over here on a contour labeled 20. We'll label that point S. Notice that the temperature is going down, so it would appear that this derivative that we're trying to come up with is negative, right? Let's see if we can come up with an estimate for the derivative. So we'll refer to those points that we labeled R and S. Okay, and the reason I chose those points is that they happen to lie directly on contours where we know what the temperature is, so it's kind of a convenient choice. So the derivative that we're looking at, or looking for at 10 and 25, is approximately the change in temperature over the change in x. Okay, that's the rate of change that we're measuring. And using those 2 points, temperature is going from 30 down to 20. So we're going to get 20 minus 30. That's going to measure our temperature change. Okay, and then how much did x change between R and S? There we have to estimate a little bit. So the x-coordinate there looks to be about 1. That's my best estimate. And what about at S? There we're getting an x value of maybe about 25 if we round. So 25 minus 1, let's say. Okay, do the arithmetic, and we're going to get negative 5 over 12. Okay, there's the numerical value of our estimate of the derivative. What would the units on this be? Okay, well, we can always get units by thinking about what the units of the numerator and the denominator are. So capital T is temperature, so that would be degrees Celsius, and x is meters. Okay, so this would be degrees Celsius per meter for our units. Okay, so we've answered part of the question. We've estimated the derivative, but they'd also like us to give a practical interpretation. What does this derivative mean in words that we just calculated? Okay, well, first thing we might want to point out when we're kind of explaining this derivative is that this is a derivative in the x direction. So that means that the t variable that we have here is constant. That doesn't change, only x is changing. Okay, so I'm going to start my explanation like this. So this means had a fixed time of 25 minutes. Okay, t is not changing. And then we might explain what's the meaning of the 10 here. Okay, well, that has to do with our position. So at a distance of 10 meters away from the heater, okay, that kind of explains these two parts of the statement. Now we want to explain what the derivative is telling us. Okay, so this minus 5 over 12 is telling us how fast the temperature is changing as we move away from the heater, degrees Celsius per meter. So we can say that something like the following. The temperature decreases, and that's the negative that we're seeing in our derivative, by about 5/12 of a degree Celsius for every meter that we move away from the heater. Okay, and notice that you can kind of see the units of our derivative in that last part of the sentence that we wrote. Degrees Celsius for every meter, that's the degrees Celsius per meter, and it describes what kind of a rate of change we're talking about. Okay, good. So we've got a value for the derivative in A, and we've given an explanation, so we're done with A. Let's move on then, okay, to part B, and I'm just going to declutter the diagram a little bit here. Okay, so B would like us to estimate the partial derivative of t, okay, at the same point 10 and 25. So now we're talking about the rate of change as time changes. Okay, so that means in our diagram we'd be fixing a value of x and moving in this direction. That's the direction of increasing time. And so we might choose ourselves a couple of points on contours again. I'm going to call these points P and Q. And as we move from P to Q, what does it look like? Is the temperature getting bigger or smaller? We started on a contour of, let's see, where is P? 20, and we wound up on 30. So now the temperature is increasing. So I would expect to get a positive number out of this derivative. Okay, so referring to P and Q, this derivative that we're trying to estimate is going to be approximately the change in time, the change in temperature over the change in time. Okay, and looking back at our picture, in going from P to Q, we went from 20 to 30. That was our change in temperature, so we're going to get 30 minus 20. And what was our change in time? Okay, well there, we need to estimate as best as we can, okay, what the time values at P and Q are. Okay, those are not nice numbers, so we'll just estimate as best as we can. Up here looks to be maybe about 57, and down here about 12. Okay, so we're going to be getting a difference in time of 57 minus 12. Okay, and do the arithmetic there, and we're going to get 2/9, and we could ask the question again, what are the units of that answer that we got? Okay, well this time we're talking about change in temperature over change in time, so we should get units of degrees Celsius per minute in this case. There's our approximate rate of change, okay, with respect to time. All right, and now we're ready to give an interpretation, explain in words what this derivative means. Okay, so this time we're taking the derivative in the t direction, and so it's the x variable that's constant, okay, that 10. So we can maybe start our explanation off by making that observation. So this means Okay, that if you're standing a fixed distance, away from the heater, at a time of 25 minutes, so I'll just say that after 25 minutes. Okay, there's the setup. And now we want to explain what the actual rate of change at this particular location is talking about. Okay, so we're getting a rate of change of 2/9 of a degree Celsius per minute. And that's describing a rate of temperature increase. Okay, so we could say that by saying something like the temperature will increase, that's the positive derivative, by about by about 2/9 of a Celsius degree. Okay, for each minute that passes. Okay, and again, you can kind of see the units of our derivative in our explanation. Degrees Celsius per minute were the units, and this is degrees Celsius for each minute. That just kind of rewords the units that we talked about above.